Welcome to our first unit on our calculus lecture series, and this first unit we are taking that of limit and continuity, as you can see on the slide. Again, I'm your tutor, Miss Egan, with the mathematics department. Let's see what we have to do under limit and continuity. Probably this first lecture video is going to concentrate on that of limit only, and the subsequent one I'll take that of the continuity, all of single variable functions. So definition, rules, and then some examples. Let's take first the intuition of limit. If you look at the images or the figures I have in slide 2, it is talking about our human life. As human as we are, what is our life progress? So you start from when you were a baby here, and then you become a gentleman or a lady, or you grow old. In this transitioning from a baby to that of this stage, what happens as we age on? Some of you say we grow old, we get weak. That is just a subsequent of it. But we also don't forget the positive side of life. We become very beautiful. We grow strong as we age on. And at long last, if you get to 80 years and above, you know there's something for you. And that is death. And so you realize that our life here, if we are transitioning as a form of our health with respect to age, we can write this as a function, the life as a function of my health. As my health approaches an age A, at age 10, at age 11, what happens to me when I get such an age? And so that is the intuition of limit. And so limit helps us to understand the behavior of functions as they approach certain values. So it helps me to understand my life. I need to understand my life health, my life as my health or as I age on. In understanding your health, it means you want to know how your health progresses as you age on. So how does my health deteriorate as I age on? So it's not when you are at age 10, but as you get to age 10. That is two different words. So the ultimate word here is approach, or getting to that certain number. Is that okay? With that intuition said, let's look at the mathematical representation of limit. So I've already described equation 1 from my limit preamble. That says as I get to a certain age, what is the behavior of my health? And that behavior is the M. That is the end point. In mathematics, I would like to use equation 2 for a general case where my f of x is a function of single variable. So the x is the single variable here. My L is the limit value. And then this is the approaching part of the function. So as simple as that with equation 2. The limit as x approaches a, f of x equal to L. I've explained all these terms for you. So A is that certain value. Having said that, we want to extend the definition with some conditions that makes it right. The condition is such that I can find the absolute between the function and then my limit. It will be very close to each other. My behavior as I approach on will be very close to each other. We say that it's less than some epsilon, where epsilons are always greater than the 0 here. And with this condition, we can be assured that our limit value is correct. Now to the remarks. The remarks is the focus of the limit. As you can see in my image, the focus is on x approach. When we have something approach mathematically, it is this arrow, the long right arrow. Yeah. It is not when x is equal to a. No. It is not when n is almost a. No. It is when it's approaching. It is not when it's even equivalent. No. It is approaching a. So that is the focus for limits. Please take note of that. I hope that has been fruitful. Let's take an illustration of what we mean by it's approaching. Let's have a function given as that. If we are asked to evaluate f of 1, you simply do a substitution because that is what we are used to. So wherever I see x, I place 1. If you do that, the numerator becomes 0, denominator also becomes 0, and you tell me this undefined. And so you tell me the function at 1 is undefined. Probably you could have looked at it in a different way. If I want to go through the algebraic approach, I could do a factorization. Which we've already gone through in algebra class, and that is it for the numerator. You realize that this and this cancels out, and I'm going to get x plus 1 as my final representation. You want to check that this factorization gives you the numerator here. If I should expand, I'm going to get x squared minus 1 plus, let me do that well. We have x squared minus x plus x minus 1. And so we have x squared plus 1, which is correct. In this, my evaluation at 1 is simply 2, because x plus 1 is 2. Hence, we can say that the limit as x approaches 1 of the function is 2. That is the intuition for the limit. Why we want to take a limit, because sometimes it will be undefined with our function, but the limit will help us get a real analysis of our function. So I'm done with the illustration. Let's quickly move to the properties. That is given in slide 6. There are basic properties we want to know. We want to first assume that our limit of any function f of x as x approaches a is L. And then the same function for a g is m. Take note of just the L and then the m. And so if I'm finding the limit of these two functions, adding or subtracting, let me add the subtraction aspect. You realize it's simply adding of the limit or subtracting the limit. If it was g plus or minus f, then I'm going to get m minus L or m plus L, because of the limits well defined. If I'm multiplying these two limits, it says simply find the limits of each other and then just multiply them. If I'm finding the limit of in a rational form, it says find the limit of the first numerator L and divide by the limit of the denominator, which is m. So that's the properties of limits. It makes it easier to just solve your functions. Again, if I have a limit of a constant k, this is the constant guy here, multiplying the function f of x, it says maintain the k, find the limit of the f of x, which is our L, and that gives you the limit at the end of the day. The last property has to do with the composite. If I have the limit of f composite of g, is the same as f limit f with the limit of g. And what does this give you? You want to try that out with the properties I have above. And that's how simple the properties are. And the last thing for the day is to apply these properties by going through evaluating of limit. In the evaluation of this limit, there are various techniques we can employ. They are grouped into two. We have the analytic and then that of the numerical. And analytic, we have substitution method, we have the factorization method, we have the conjugate. And I hope you remember conjugate factorization in algebra. Yeah, in algebra. Conjugate comes when you have sets. Factorization is mostly for polynomials or rational functions, which still deals with polynomials, and substitution is just throughout. And the numerical aspect will take tabulation, which I'll do as my next lecture video for you. Now, someone may ask, what are the kind of functions we are going to deal with? These functions can be polynomial, it can be sets, it can be tricks, it can be rational functions, it can be exponential functions, it can be logs. All these functions we can find the limits of them. And so let's quickly take one or two examples on the method. So I'll first start with the direct method. Let me just have a full version of it. Yeah. So I'll take example 1. I have a function given as x approaches 5. This is a polynomial. You know why it's a polynomial. If you're not sure, you can go through the algebra lecture videos on polynomials of degree 2. So it's quadratic. If I want to find as x approaches 5 here, because it's a polynomial, I can do a direct substitution. Again, because it's a polynomial. So with a direct substitution, wherever I see x, I place 5 there. Wherever I see x, I place 5. And then For sure, I'm going to get 39. If that is right, you are good. If not, you can correct me in the comment section. So that's how simple this limit would be. If I take example 2, this is a polynomial of another polynomial. So I say P over Q, and you know there's simply a rational function or a rational expression. We've gone through that. Given that the denominator is never equal to 0, that was the extra condition. And so if you want to find the limit as s approaches negative 2, please do not do a direct substitution yet. You want to check the denominator. Let's do a check here. You want to ensure that it is never equal to 0. And so if I substitute negative 2, I'm going to get, since this is minus, I'm going to get 11. So 5 plus 6, that is 11, which is never equal to 0. So we are good to do a direct substitution. Okay, so wherever I see x, I place the negative 2. So this guy comes here. This guy still comes here. And then over 11. I'm not so sure what I'm going to get, but at the end of the day, this goes to 0. I have negative 1 over 11 as a final answer. So that is how the substitutions is done. You must check certain conditions. The last example, if I want to have the limit as x approaches 3, again, because it's a rational function, please don't do a direct substitution. Check the denominator. Let's do a check. And what do you get? You know the answer. So that is it. The answer is, are you sure of what you've had? Yes or no? Then the next item is factorization. Let me extend the entire slides. Slide 9. I want to take the first example. I'm giving as x approaches 3 here. You know that since there's still rational function, I must check that my denominator q is never equal to 0. If I do a substitution here, I will end up getting 0. That's 3 minus 3. And you know any number divided by 0 is undefined, which we want to avoid. So what can we do? Again, we can do a factorization here. And what does this get you to? The roots of polynomials, x minus 1, x minus 3. It should give you the numerator. You realize that this will now cancel that, and I'll have x minus 1 as my final representation. And so the limit as x approaches 3 will be equal to 3 minus 1, which is equal to 2. And that is my limit. The second example, this is still rational. For if I do as x approaches 1 and I do a direct substitution, I'll end up with the division of 0. You want to think through this as I have the image there for you. And so let's do factorization. That is if possible. If not, the other ways. The factorization here becomes x minus 1, x plus 1. You check it out for me here. And then this will cancel the first one. I'll get x plus 1. And so what is the limit of this function as x approaches 1 of x plus 1? I'll end up getting 2. For example 3, I'll leave it for you to check it out. Always check the denominator. Ensure the denominator is not equal to 0, and you'll be good to go. And so that is it for factorization. Now let's move to one important message before we do the conjugate. We have one with when probably you can look at direct factorization and then the conjugate. Factorization. If I have this, you know, I can easily check the denominator here. It will not be equal to 0. It is equal to 8 as x approaches 4. And so it means I can do a direct substitution here. Wherever I see x, I place 4 in there, and I end up getting 2 over 8 over 8, and that gives me 1 over 16. If you don't want this direct approach, and you want to use the LCM, you know what the LCM means. I have to find the LCM for the numerator, which is here, and then the denominator also comes here. From here, you can simply do your algebra, and trust me, you end up getting the same answer. How do you do this? I do a cross multiplication up here. Is by 1 all over these two guys. This is what I have. And so by substitution, denominator will never go to 0. So I can simply put x 4 times 4 into bracket 4 plus 4. 4 plus 4 is 8. 4 times 4 is 16. And then don't forget the numerator also adds up to 8. So I end up getting 1 over 16. Now the last property is the conjugate. If you've forgotten what conjugate is, don't worry, I still have the lecture videos for you on sets and you can check it out. Someone will say, I want to do a direct substitution. Okay, let's see what happens. Because it's approaching 0, it means you're going to get something up here over 0 squared is 0. And this is an undefined function. You want to always avoid undefined. And so think of the other things. Since that already didn't work, you had factorization. Can you factorize this out? If you can, you are good to go. If not, think of something else. Now let's use conjugate. Why? Because I see the radical functions here. That is the third function given. How do you find conjugates? I know you know, so let me quickly go through that for you. I have x squared plus 9 plus 3. The sign here changes. And you know conjugate, you must multiply through the function by it. Okay, so it is plus 9 plus 3. You multiply by the functions. And so when I do the expansion multiplication, these are now two polynomials you must multiply. I'll end up getting this one. Please take your time and go through the multiplication. You must get what I have here. And this is x squared plus 9 plus 3. Not minus 3 plus 3. And so let's continue. Because I have positive 9 here, negative 9 here, they go to 0. I end up getting just x squared. And then I have x squared here as a denominator. What happens here? Realize that I can cancel these guys out. And I'll end up getting 1 over the square root of x squared plus 9 plus 3. But here I can do the direct substitution. The square root is just on x squared plus 9. So with direct substitution, I get 1 over the square root of 0 plus 9 plus the 3. And square root of 9 is 9. So I get 1 over 6 as a final answer. It means I'm looking at the limit as x approaches 0 of this new function, which is now 1 over 16. So always check for these methods we've gone through before you conclude that it is undefined. Now to the best part of my teaching is the problem of the day. You must understand whatever we've gone through and be able to apply. That is the beautiful aspect of knowledge. So let's look at the problem of the day. It is said that you have a production firm. That is a preamble what it's about. It has a cost function, it has some revenue function, it has some production of S units, and you are asked to find the company's profit if they're making a projection of producing 8 bags or 8 units of whatever product you have. What is the projection here? And so realize that in production there are things you want to consider. You always want to know the total cost of production. How many goods are you producing? What is the unit price of producing each of these products? What is the sales? That is the revenue. And the almighty above all, you must make profit and you must not run at a loss. Now from the preamble, the total cost is given. Yes. Is the quantity given? Yes. It says some 8 quantities. Is the unit price given? I'm not so sure. Is the sales given? No. The unit price is given here. The price function is given. But we are asked to find profit. And so how would you do that? Now you know that profit is not a straightforward question. Profit is revenue minus total cost. So the revenue function minus the total cost function. So profit of producing X goods, that's why I have the X here, is the revenue of producing that X, selling that X goods, minus the total cost of producing. So here is selling and here is producing. So how do you get the revenue function? It is the quantity of produce times the price function. We always know this. And so the quantity is given as 8. You must now know how to find the limit as x approaches 8 instead of 5. It is 8 here. So what is the projection of profit for 8 bags? You must have this price function minus the total cost. It is already given in the preamble. You must figure them out. I have 2 preambles given. I have 2x plus 10 and I have 2x plus 10 and then I have 20 plus x. Which of them is the price and which of them is the total cost? If you figure this one out, you can simply find your profit function and then see if you can have a direct substitution or factorization to find a profit after 8 units. And that brings me to the end of this limit. In the next unit, we're going to take out the numerical method. Thank you and stay tuned.